Hi, Assalamualaikum warahmatullahi wabarakatuh and a very good morning to everyone. My name is Muhammad Hafiz bin Rosle, metric number DE180159. So today I will explain more about the final project 2 regarding the experimental result based on the final project 1 simulation result. So welcome to our panels. I am Dr. Hisham bin Rahman and technologist Muhammad Hafiz bin Ismail, also to our supervisor, which is Professor Madya, technologist Dr. Asmar Rashid bin Poniran. So the project title is about a design of cascaded multi-level inverter topology for integrated portable power pack application. So in this video is divided into few parts, which is the first one is a project background, problem statement, methodology, simulation result, and experimental result. So the project background, problem statement, methodology, and simulation result has been discussed in the final project 1 video, but I will explain briefly about this, and we will go deep into the experimental result. So firstly, we go through briefly about the project background. So the project background about the design of cascaded multi-level inverter topology for integrated portable power pack application. So what is a portable power pack? So a portable power pack is a device which supply electrical power to users' electrical appliance at anywhere. So this device usually can be used at a 5V DC device, 12V DC device, and 240V AC appliance. So there are wide range of voltage output is important to be used in a variety of application. However, there are a few of a problem to invent a portable power pack. So most of electrical appliance need an AC voltage source to work properly. Just they need an inverter to convert from DC to the AC voltage. So the inverter for the portable power pack in the market is not efficient. It has a high THD, big filter, and this causes the electrical equipment to not work properly. So the possible solution for this problem is by implementing a cascaded multi-level inverter for the method to improve the inverter quality. So the multi-level inverter works by increasing the level of the inverter. So the higher the level of inverter, let's say from 3, 5, 7, 9, 11 and so on, so the lower the THD percentage and the filter size, also the efficient of the inverter. There are three objectives for this project. The first one is to minimize the voltage THD and the size of output filter of the inverter by implementing a cascaded H-bridge multi-level inverter. The second is to develop a circuit models of the inverter by applying a specific level of cascaded H-bridge multi-level inverter with suitable switching technique. The third is to evaluate the THD result of the cascaded H-bridge multi-level inverter based on the output voltage level and switching technique. Moving on to the scope of project. So the project application is restricted to low power applications such as electrical gadgets and low electrical appliance that less than 500 watt. So the project will use a typical H-bridge multi-level inverter topology design to develop an inverter. So the simulation system will be running on a various software such as MATLAB, Arduino, Quartus Prime, Fluke Power Analyze, PCWiz, and Proteus 8 Professional. So the four is a performance analysis such as voltage, current, and THD percentage will be ensured. The fifth and the last is comparing different methods to control inverter power and effect on different level of the inverter. However, in designing of the multi-level inverter has also a few issues. So there are a few issues such as the first one is the high THD, which can be solved by the increasing the output level. And the second was the high number of semiconductor devices. So we know that the multi-level inverter also can be increased the THD by increasing the level of inverter. But when we increase the number of level inverter, we also increase the number of semiconductor devices. So this can be solved by the selection of modulation technique, such as the PWM or SPWM. Okay. The third is the high semiconductor losses and low efficiency. So when the number of semiconductor is increasing, there's also a chance for the semiconductor to has a losses and in the switching losses, and also can affect the efficiency of the switching. Okay, this can be solved by the reduction number of semiconductor devices. Let's continue to the methodology part. So the methodology will explain on how I make the portable power pack in designing from the first step until the last step of the design of the multi-level inverter. Okay, this is the complete system for the integrated portable power pack. There is a TNB supply, battery charger door, Arduino for the locking system and so on. But the things that to be highlight is the inverter which located in when the DC voltage is changed to the AC voltage supply. So this is the zoom in of the inverter system, that we need a battery to supply, and we have the buck boost converter to regulate the voltage to be higher or lower, and we have the ceiling to what we call to stable the voltage output from the DC supply to the inverter itself. And in the cascaded multi-level inverter, we have the microcontroller unit which determine the switching technique for the multi-level inverter, and to control the MOSFET, which is a semiconductor devices, and we have the filter to minimize the THD, and we have the AC load. So this is the flowchart for the inverter system in designing of the multi-level inverter. So the firstly, we need to identify the required load voltage. It can be 20 volt, 24 volt, 5 volt, 240 volt, 230 volt, and so on. And then we determine the optimal voltage level and the number of switches that need to be used for this design. And we choose the method to control the switches. So as mentioned before, this multi-level inverter can be controlled by a few methods. So in this project, I will choose two types of control method to control the multi-level inverter. So the first one is by using the PWM, which is the pulse width modulation, and second is the sinusoidal pulse width modulation, which is the SPWM. Then lastly, we observe the voltage, current, and THD percentage at the output of the inverter. Okay, continue to the simulation result. So actually the simulation result has been discussed in the FFP1 video, but I will briefly explain the result of the simulation, and not explaining the circuit diagram and so on. But the highlight of this simulation result will be based on the level of inverter, which is from the 3, 5, 7 level of cascaded H-bridge multi-level inverter result. So this is an example for the cascaded H-bridge multi-level inverter with a PWM switching technique. So as I mentioned before, there is a two method of switching technique, which is the first one is the PWM, and the second one is the SPWM. So this is the PWM switching technique circuit, that actually we have the pulse generator, and we have the MOSFET, we have the DC voltage, and we have the load. Okay, the difference between the 3 and 5 level of cascaded HP multi-level inverter is the number of components, the number of DC input. So as we can see here, when the 3 level, we have only one of DC input voltage, but for 5 level, we have two of the DC input voltage, and also the number of semiconductor is increasing from 4 MOSFET to 8 MOSFET. Okay, let's continue in the cascaded H3 multi-level inverter with the SPWM switching technique. So in this SPWM switching technique, the difference between the PWM and SPWM is we have two signals here. For the PWM, we have one type of signal, which is the pulse generator, but for the SPWM, we have two types of switching. We have two types of signal, which is the first one is the sine wave, and the second is repeated sequence. So this signal will be compared and will send into the MOSFET. Okay, so the difference between 3 level SPWM and the 5 level SPWM is also the number of input voltage. You can see here, when the 3 level we have one input voltage, when at the 5 level we have two input voltage, and also the number of semiconductor is increasing from 4 to 8 semiconductor. Then we jump into the inverter parameters and performance comparison between the number of level of the inverter and the switching technique for the inverter. So at the 3 level of the inverter, multi-level inverter, the number of voltage source is 1, number of switch is 4, and it producing 52.06% of the THD voltage. Then at the SPWM inverter, we have identically same number of the THD. But at the 5th level of the inverter, the number of DC voltage is increasing to 2, and we also have 8 number of switches. Then the THD is different between 29 and 98% at the PWM inverter, and 26.84% for the SPWM inverter. Then lastly, at the 7th level of multi-level inverter, okay, the number of DC voltage is increasing to 3, and number of switches is also increasing from 12. And also the THD of the inverter is decreasing from 29.98 to 29.94 for PWM inverter, and from 26.84 to 18.2% of THD voltage for the SPWM inverter. So the most suitable inverter level is the 5 level of Cascaded HP multi-level inverter with PWM switching technique. The reason behind this is because when I choose the 5 level Cascaded multi-level inverter with the PWM switching technique is because the PWM has less complicated than an SPWM switching technique. So when we choose the PWM switching technique, it has a low semiconductor losses, because in the SPWM it's much complicated because it has two of signals, which is the sine wave and a carrier wave signal. And also the 5 level inverter of the with the PWM switching technique has a 42.4% less THD compared to 3 level of Cascaded HP multi-level inverter. Okay, lastly, because it has a less number of semiconductor devices compared to the 7 level of Cascaded HP multi-level inverter. So for the 5 level of Cascaded HP multi-level inverter have 8 number of semiconductor devices. However, for the 7 level of multi-level inverter has 12 number of semiconductor devices. Okay, lastly for the experiment result. So in the experiment, I will choosing the 5 level of Cascaded HP multi-level inverter with PWM switch technique. Okay, this is the experiment setup that we have a few instruments here. So the first one is the laptop that use connected with the power recorder to monitor the THD, and we have the DC power supply, we have the power recorder itself, the fluid power recorder, and we have the oscilloscope to monitor the waveform, and we have the load. There are two loads. So the first one is the variable resistor at the back, and we have the AC fan as the electrical appliance load. And the most important is the 5 level Cascaded HP multi-level inverter circuit, and we have the gate driver unit, and we have the microcontroller unit. So this is the experiment result, that we have two result here, which the first one is by using FPGA, and the second is by using the Arduino Mega 2560. So the reason why there are two types of the result here, because at first I want to use the Arduino Mega because it is a simple, compact, and easy to be coding. And the drawbacks of using Arduino Mega is because it can produce only up to 60 Hz of frequency. But for the FPGA, it can produce up to 50 Hz of frequency. But the drawbacks of using FPGA is because it large and not suitable for our project. As you can see here, the output voltage here is showing the FPGA output voltage is around 234 volt RMS, while the Arduino Mega is producing 232 volt of RMS, and the current draw is almost the same, 0.5 amp and 0.9 amp respectively. But the difference here is the output frequency. For FPGA is producing 50 Hz and Arduino Mega producing 60 Hz of frequency. So this is the results after we connected the inverter with the AC load, which is the stand fan that rated for 55 watt. And the result for the FPGA, the output voltage is about 196.57, and the current is 0.52. Then the frequency is same at 50 Hz, but for the Omega is 60 Hz and 188.76 of volt RMS and drawing 0.51 amp of current. So the reason why the voltage is dropped from 230 volt RMS to 190 volt RMS because of the transformer itself. So maybe this transformer is not suitable for this type of wave. So maybe it may works properly when we are using the sinusoidal output voltage to be used at the transformer. So this is the output current waveforms for both of the microcontroller by using FPGA and Arduino Mega. So we can see here there is no large difference between 50 Hz of frequency and 60 Hz of frequency. Then this is the most important part of the experiment, which is to observe the output voltage THD and the output current. But the output current can be reduced by using the filter, but I'm not using the filter for this project because I intended to focusing on the THD voltage only. So on the left side of the screen is the FPGA result, and on the right is the Arduino Mega result. So we can see here the voltage THD for the FPGA and Arduino is same at the 30%, producing 30% of voltage HD, while the current for the FPGA and Arduino Mega is slightly higher at the Arduino Mega, which is 36%, and for FPGA is 2% lower, which is 34%. So in the conclusion, I can say that the circuit models is working properly because the voltage HD for both FPGA and Arduino Mega are producing almost the same as in the simulation result, which is in the simulation we're producing about 29% of voltage HD, while in the circuit models producing about 30% of the voltage HD. And lastly, for the result of the comparison between the THD percentage against the experiment type, so actually I have done a few of experiment, such as before connecting the inverter with the transformer and before connecting with the transformer to producing 230 volt or RMS. So the highlight of this table is comparison between by using the FPGA and Arduino. So as we know, the FPGA can produce up to 50 Hz, but for Arduino, it's capped at only 60 Hz of frequency. But after we done the experiment, we can see here that the THD is not THD percentage of both microcontroller have the same result, which is between 36 and 34% when we connected with the load. And before we connect to the load, let's say at the 24 V peak, the percentage is almost the same at 28.4 and 28.3% of voltage HD. So this is why in the Malaysia we can use 50 or 60 Hz of frequency at the electrical appliance, because the difference of frequency in 50 and 60 Hz does not affect the quality of waveform. So I think that's all for this final project 2 video presentation. So if you have any question, do not hesitate to ask me or call me regarding about the final project. Okay, thank you. Bye bye.